Welcome to physics class on current and electricity, and in today's class we will try to learn the first 2 points. That means the first one is Kirchhoff's law of electricity, and in the second we will try to learn about the Wheatstone bridhe. So the first one is the Kirchhoff's law of electricity. In Kirchhoff's law there are two laws. Okay, the first one is known as Kirchhoff's first law, or we can call it as Kirchhoff's current law or junction rule. So this first law we sometimes call it as KCL also. That represents what? K for Kirchhoff, C for current, and L for law. So KCL or first law, or simply as junction rule. So as the name suggests, it is concerning about the junction in an electrical network. Okay, in an electrical network, what happen of circuits, if those currents at a network at a junction, the algebraic sum of the currents at a junction is always equal to 0. Suppose if there are some currents coming toward the junction, so let's take it that O is a junction at this point. So if I1 and I2 are coming toward the junction, then and some of the currents are also going away from the junctions. Let's take it in this way. These currents are going like this: I2, I3, I5. Okay, these currents are going away. So what happened? The algebraic sum of all those currents, okay, at a junction, this will be always equal to 0. So when I say algebraic sum, then we have to assign plus or minus. Okay, so which current should be assigned plus and which current should be assigned minus. So all those currents coming toward the junctions, that means incoming current, will be assigned positive, and those outgoing, that means going away from a junction, are assigned what? Negative. So coming in, that means getting toward the junction, that will be taken as positive, and going away from the junction, that will be taken as what? Negative. So what happened? The mathematical expression is this: I1, I2, I3. These are all the currents coming or going away at a junction. So what happened? I1 and I4, this will be assigned positive as they are coming toward the junction. Those current I2, I3, I5, those going away from the junction, will assign what? Negative, like this. So the algebraic sum of these will be equal to 0. In another word, we can say that instead of saying like this, instead of saying the algebraic sum of a current at a junction in any electrical network is 0, instead of saying like this, we can also say that the sum of the incoming currents is always equal to the sum of the outgoing currents at a junction. Got it? So from where this law comes? It comes from the conservation of charge. So in a closed circuit, what happened? There will not be no undue accumulation of charge at any point onto that electrical circuit. When I say electrical circuit, it should form a closed loop. Okay, then what happened? If current moves in that closed loop, then whatever the current that it goes or it passed through a point, that much current should also leave it. If it comes with some current, that much amount of current should leave it. In another word, in terms of charge conservation, actually this Kirchhoff's current law, it comes from the conservation of charge. Okay, whatever the current that is coming, it is due to the flow of charge. So whatever the charge that cross through a particular point, that much charge must also leave that particular point. Charge coming through a particular point, that much amount of charge should leave that particular point again, or you can say through that cross-sectional area. Got it? Next is your Kirchhoff's second law, or we call it this Kirchhoff's second law also as KVL, Kirchhoff's voltage law, or loop rule. So this is concerning about the loop rule. So the statement will be given like this: the algebraic sum of all the potential drop across the resistors and source of EMF along any closed path in an electrical network is always 0. So the algebraic sum of potential drop or potential difference across resistors and cell, okay, the algebraic sum of these potential drop across resistor and cell, this will be always equal to 0 in a closed loop. Okay, mind you, this is very important, in a closed loop. So let's take it this closed loop A, B, C, D as it is shown here in a clockwise direction. Then what happened? In this loop direction, the potential drop across this E1, that means through the source of EMF, this cell itself is denoted by E1 and its EMF is also again denoted by E1. Okay, so across this cell E1, what sign should be assigned? Okay, what sign, whether it will be positive or negative, should be given to this source of EMF? That is a question. Okay, if the EMF is taken, the EMF of this source of EMF, this cell, I mean the EMF of this cell E1 will be taken negative when we traverse from positive to negative. Okay, positive to negative terminal. Okay, negative terminal of the cell through the electrolyte of the cell, or rather inside the cell itself, not from outside. Okay, inside the cell. So if the loop or the EMF is taken negative, when what happened, we traverse from positive to negative terminal of the cell through the cell itself. Okay, or you can say through the electrolyte, otherwise it will be taken as what, positive. So if we traverse from negative to positive terminal inside the cell itself or through the electrolyte, then that will be assigned what, EMF positive, otherwise it will be negative. Okay, so in our case, what happened, it travels from where to where, positive to negative terminal through the cell itself or through the electrolyte, so we have to assign negative. Got it? And let's now go to the potential drop across resistors. What will be assigned to the potential drop across these resistors, whether it will be positive or negative? Now, if we know that the potential falls along the direction of the current in a current path. Okay, the potential falls down along the direction of the current in a current path. Now we know that current flows from higher potential to lower potential, right? So that means current, the direction, the potential, now here it goes from the high potential to low potential, right? So that means it falls down. The direction of the current in this, it falls down from where to where, from this high potential to low potential. So if the current falls down, then we have to take it as negative. If the direction of this current is from higher potential to lower potential, so high to low, negative, that means current falls down. Okay, or rather we can call it as potential falls down from high potential to low potential. So low means what, negative, or falling means negative. Or in another word, on the other hand, what happen, if the potential rises? Okay, if the potential rises, when the potential will rise, when the potential will rise from the low potential to high potential, if the direction, or if we move from low to high potential, then what happen, it will give as what, positive. Low to high means rises. When the potential rises, then the potential drop across R will be taken as what, negative, positive. Low to high means potential rises, right? Potential rises. So in that rises, we will give it as what, the potential drop, that means I1 times R1, like that, current and the product of the current and the resistance. Okay, that product will assign positive. I'm telling you again, if the potential falls, okay, if the potential falls along the direction of the current, then we have to assign negative. Falling means negative. And if the direction of the potential, if the potential rises, that means along the direction opposite to that of the current, that means from low to high, like that, then we have to assign what, positive. Why? Because potential rises from low to high, like that. Okay, in that case we have to take as what, potential drop across that resistor as positive. Okay, so now let's see in the latter part of this I will tell you the simplest and the easiest mnemonic, okay, and that will be the applicable for numerical calculation also. Let's see for the second loop, okay, let's take it that second loop as A C D A, okay, in this clockwise direction. This one is also clockwise, I'm taking here also clockwise, but you can take it anti-clockwise also, no doubt. It is independent of the direction of the loop, okay. Yes, we are taking like this, and in this also the loop direction A C D A like this. So this is also in the clockwise direction, and the mathematical expression will be what? Minus I1 minus of I1 plus I2 times R2. That means the potential drop across R2. Here you see it will assign negative. From where to where? It is coming from this to this. Got it? Minus here like this. So from high to low, so it will be what? Assign negative. That means potential falls. If potential falls, that means it will be negative. If potential rises, then it will be what? Positive. But here it is potential falls. So your I2 times R3 here also it will assign negative, and here through the electrolyte it goes from what? Negative to positive. So we have to assign E to positive. So this will be equal to 0. Okay, but this is all about the Kirchhoff's voltage law or the second law or the loop rule. Okay, so what to assign here, whatever I have told you, it will be all here. So the EMF is taken negative when we traverse from positive to negative terminal of the cell through the electrolyte. Okay, through the electrolyte means inside the cell itself. Okay, and it will be taken positive if it travels from negative to positive terminal inside the cell or through the electrolyte. Got it? And this is about your EMF, and the latter part is for your potential drop across the resistor. The potential falls along the direction of the current. Falls means what? From high to low. Okay, in that case falling. And when the potential rises means from low to high. Got it? So falling means, potential falling means what? It will be taken as negative. Potential rising, okay, along a direction opposite to that of the current. Got it? That means it is rising if the current moves like this, and if the loop is moving in this way, then it will be rising. Got it? If the potential rises, then what happen? Potential rises should be taken as what? Positive. Okay, for this, what happen? Whether it will be this direction, if you take it this direction also, what happen? It will be having the same equation like this, and if it is anti-clockwise like this also, it will be having the same equation. In that case, the only thing is that what happen? This sign will be changed. If it is anti-clockwise loop, then E1 will be what? Positive, and the product of this potential drop across R1 and R2, this will become negative in that anti-clockwise direction of the loop. Got it? If it is like this in this anti-clockwise direction, A, C, B, A, in that case this will be positive. Why? Because it moves from negative to positive in the loop direction, I mean, that will be positive. And this potential drop across R1 and R2, this will be negative. Got it? Negative. Why? Because potential falls. Okay, if it in that direction, that means potential falls, so it will be what? This will assign negative in that case. Got it? If it's moving like this in the anti-clockwise direction, right? So it is independent of the what? The loop direction, whether it is clockwise or anti-clockwise. But I'm telling you the simplest one, just to remember the mnemonics. Okay, now you take it in this way. Instead of having the algebraic sum of all the EMF and the potential drop across resistor is equal to 0, now you try to separate the potential difference across a resistor and the EMF of the cell. The potential across the source of EMF and the potential drop across resistor. Got it? You try to separate it, and let's try to write the source of EMF okay, the potential drop or the EMF across the source of EMF, that one you try to write on one side, and the potential drop across resistor on one side. Got it? This is what potential, okay, difference across what R. Let's try to write on one side, and the potential across the cell, that means source of EMF, you try to write it on one side, and let's try to equate these two by equality sign. Okay, so what happened? The potential difference across EMF, what sign, plus or minus, should be given? I will tell you that one. If the loop direction is starting, let's try to say starting from A B C A, right? So the loop direction is in this direction, AB. So if the direction of the loop, okay, is going from positive terminal to the negative terminal, then negative, the last, okay, electrode, positive electrode, negative electrode. If it comes negative, then you have to take it as minus to that of E1. Positive to negative, then you assign negative. If it is from negative to positive, then the last one is positive. From negative to positive, then you have to assign positive. But in our case, the loop direction is from positive to negative, so we have to assign negative. Now let's try to find out the potential drop across R. Now what sign should assign to the product I1 R1? The current flowing through R1 is I1, so the potential drop across R1 will be I1 R1, and the potential drop across R2 will be what? Current flowing through it is what? I1 plus I2, right? This is the current flowing through what? This is the current flowing through what? Current flowing through R2 is what? I1 plus I2. This is the current that flows across what? R2. So the potential drop will be I1 plus I2 times of R2. So the question is what sign will be given, positive or negative, to this potential drop across R1 and R2? I'm telling you the mnemonic. Now if the direction of the loop, okay, and the current given in the circuit, if they are of same, then we have to assign positive. If the loop direction and the given direction are opposite, then we have to give negative. Now the loop direction is from A B C A, like this. That means across through this branch, it is in the direction from A to B, right? In this direction, in this way. So A to B. But the current direction in the circuit is from B to A. They are opposite, right? Loop direction is from A to B. Current direction given here, I1, is from B to A. So they are opposite. If they are opposite, then we have to assign minus. Got it? If they are along the same direction, parallel, then we have to assign what? Positive. Same means positive, opposite means negative. What opposite? Loop direction and the given current direction in the circuit. So loop direction is from A to B, given current in the circuit is from B to A. They are opposite, so we have to assign minus. And for this potential drop across R, let's see, loop direction is from C to A, through this branch, I mean from C to A, loop direction. Got it? But the direction of the current in the circuit is from A to C, again opposite, right? So we have to assign again negative here. Got it? So if you do like this, then it will be very easy to remember. Now here let's try to see that even though if I am taking like this, it will be same with that one that was given here in the first equation for this loop. Okay, A B C A, the first loop I will call it. So if you try to express this now in this form, then you try to transfer this, okay, expressions on the right hand side to the left hand side, then you will get like this. This minus will come plus when you transfer to this side, right? Got it? Then you will get this first equation. So it is very easy to remember with this one. Got it? You try to write separately. What? Separate? Source of EMF. Okay, the potential drop across the cell on one side and the potential drop across the resistor on the other side. Got it? If you try to write like this, then it will be very easy to remember, right? Now let's try to find out for this second loop. Second loop is also ACDA, right? So what happened for the source of EMF? Let's try to write the source of EMF first. So the loop direction is in this direction, ACDA, like this. That means through this branch it moves from negative terminal to positive terminal, right? So negative to positive. So we have to assign what? Positive. No need of writing plus, but for the time being, let me write as positive. So it will be what? E2, positive E2, right? And let's try to write for the potential drop across the resistors. Now we need to see the loop direction and the given direction are the same or not. If they are same, loop direction is from A to C, current direction is also from A to C. So we have to assign what? Plus or minus? Yes, plus. So it will be assigned plus. Let me write plus. Okay, so I1 plus I2, right, times of what? R2. This is the potential drop across R2. Why we assign positive? Because the loop direction and the given current direction are same. Got it? And what about here? Across this R3, loop direction is also like this, ACD, like that, no? And the current direction given here in the circuit is also same, from C to D. So loop direction and the current direction are same, so we have to assign plus. So it will be given plus of what? I2 times R3. Now again, this will be also having the same as it was given in the second equation here for the loop, second loop, ACDA. Now if you transfer this to that side on the left hand side, then you will get it this one. So this one is very easy to remember. Got it? Yes. These are the things that I have given you. Okay, if you want to note down, then you can note down it by pausing this video. Okay, now let's try to learn about the last part. Okay, the last part is what? Your Wheatstone bridge principle, or Wheatstone bridge simply. Now what is this Wheatstone bridge? You know, four resistance connected on the sides of a quadrilateral so as to form a bridge, which enable us to determine what a non-resistance. Okay, that circuit we call it as Wheatstone bridge. Okay, so these are the four resistors, P, Q, R, S. These are the four resistors so as to form the sides of a quadrilateral. Okay, and if in this way, if the potential, okay, at the opposite vertex are same, if the potential at this point and opposite vertex means this one, so if the potential of the two opposite vertex are same, then the ratio of one side of the resistance will be equal to the ratio of the resistance on the other side. Okay, this principle, when the potential drop across the two opposite vertex, if they are same, then we call it that as what? Wheatstone bridge, as what? Balance bridge, we say it. Got it? If it is of balance bridge, then the ratio of the resistance on one side will be equal to ratio of the resistance on the other side. So how to prove this? This will prove from that Kirchhoff's law. Okay, Kirchhoff's, either we will use both Kirchhoff's current law as well as Kirchhoff's voltage law. Now if you take it those loops directions in this way, then it will be in the way given in the equation here. Now see, applying this loop rule, that means your Kirchhoff's second law in this loop A B D A, then you will get this expression, right? You just try to apply that Kirchhoff's second law across this through this loop, okay, in this loop. Okay, let's take this loop as A B D A like that, then you will get like this. For the loop here in the second loop also, if you take it that Kirchhoff's second law, if you apply it, then you will get like this. But when the potential B and D are same, there will not be no current through this galvanometer. Okay, G represents galvanometer, so your Ig will be equal to 0. If you put that Ig equal to 0 in this above two equation, then you will get it what? The resulting equation. So when these potential B and D, okay, the opposite vertex of this quadrilateral, if their potential are same, then we call it that as what? Wheatstone bridge, as a balanced bridge. So in that balanced conditions, what happen? No current will be flowing. So in this equation, your Ig part will be equal to 0. Then what happen? On simplification, you will get like this: P by Q will be equal to R by S. P by Q will be equal to what? R by S. So these are, P by Q is nothing but the ratio of the resistance on one side. If you take it this as the middle part, and the ratio on the upper, okay, side of the resistance, upper side means P by Q will be equal to ratio on the lower side, R by S. Okay, P by Q will be equal to R by S. Or you can take it this as the middle line, and you can take the ratio P by R equal to Q by S just from this. Okay, you know how it is coming. So by putting what? Ig equal to 0 in this equation, then it will come like this, the first equation. Okay, so you try to find out P by R from here, then it will be I minus I1 divided by I1. From the second equation, if you put that Ig equal to 0, then you will get like this. So these two right hand side are equal. Naturally your left hand side must be also equal, right? P by R will be equal to Q by S. So on simplification, you will get like this. Got it? That's all for today. Okay, thank you.